This video demonstrates how to do a power calculation. As a quick review, alpha is the probability that you reject the null hypothesis, assuming that it is actually true, what we would call a type 1 error, rejecting the truth. 1 minus alpha is the confidence that your conclusion is actually correct. Beta is the probability of a type 2 error, that is, failing to reject something that is actually false, or the null is not true, but you fail to reject it. We are going to look at an example of a hypothesis and a sample. You start with a hypothesis and you end up with a sample. If your sample is true, quote unquote, but it doesn't make it into the critical region, then you fail to reject the null, which means you fail to reject something that is actually false, something you would want to reject, a type 2 error. Here we have a problem from WAMAP. We're working with the given hypotheses that the null is that the population average is 40. The alternative is that the population average is actually greater than 40, where the null population is assumed to have a standard deviation of 6. We're working with a significance level of 0.05. We obtain a sample of 34 with a sample mean of 42.8. We can estimate the power by assuming that the real population has a mean equal to that of the sample. In some ways, this actually makes sense because the sample mean is more concrete or authentic than is the null mean, which is sort of a number that was just created or pulled out of the air. So I have input here in Excel a number of the key values. The first question is to determine what is the critical z-score for this right-tailed test. And this would be equals norm S_inv for 95%, because we want 95% of the values to the left, indicating the region in which we would fail to reject the null, and only 5% of the area to the right, which would be the critical region in which we would reject the null. If we were to actually calculate this as a value, this would be the z-score times the standard error that we calculated plus the hypothesized mean. Okay. This now plots the point on the curve. The blue curve indicates the null hypothesis, and the red curve indicates the curve that would be associated with the sample mean. Notice this sample mean curve is centered at about 42.8, whereas the null hypothesis curve is centered at 40. The second step is to determine what the standardized critical value would translate into for the hypothesized sampling distribution, and that's where we use the z-score of 1.644 and change, converting that back to an actual average score of 41.69 and change. To reiterate, when we're talking about confidence and significance, significance is the probability of rejecting the null, which means a value would fall in this critical region here. Significance is making an error where the null is true, but we actually reject it. The confidence that we wouldn't do that if the null is true would be 95%, 1 minus the significance. Step 3 asks us to assume that the real population has the same mean as the mean of the sample. Using this new sampling distribution, which is centered at the new mean of 42.8, what z-score is associated with this critical value that we calculated for our hypothesis? Well, this would be the equivalent to taking the score 41.69 and change, subtracting the sample mean of 42.8, and dividing this by the standard error. That has a z-score of negative 1.076 and change. The probability of selecting this score is norm S_dist, which turns out to be a little over 14%. Power is 1 minus this value. Okay. And let me reiterate again what the beta value actually is. Beta is the probability of failing to reject the null if the null is actually false. In this case, we're assuming that the sample actually indicates the truth. The probability of obtaining a sample mean that would lead to failing to reject the null hypothesis would be this area here. The value is less than 41.69 and change. The likelihood of that happening is about 14%, which means the likelihood, and again, to reiterate, if we found a value here, we would fail to reject the null because it would not fall in the critical region. But if the red curve is correct and the blue curve is the null hypothesis, we actually would want to reject the null because the actual population average is larger than 40. So if we end up with a value here, we fail to reject the null, which is incorrect. So beta is the probability of making a type 2 error. Power is 1 minus beta, the area on the other side of the curve. So in truth, the likelihood that we would actually have rejected this null hypothesis, that the mean is greater than 40, would have been about 86%, or 1 minus 14%. The significance, again, is the probability of rejecting the null when it's true. Power is the probability of rejecting the null when it is actually true. Beta is the probability of failing to reject the null when it's true. So this is a quote-unquote error region, and this is a quote-unquote error region.